voltage divider biasing. Before notes 12, before voltage divider biasing, the kind of circuit we built this week in the lab and last week in the lab was a base biasing circuit, if you recall. Okay? With a voltage divider biasing, look at figure 1. Look at figure 1. If you don't have a copy of the handout, come and get it. Figure 1, in figure 1, do you see the voltage divider circuit, which is shown in gray, R1 and R2? R1 and R2 is the voltage divider circuit, and what you're doing is you're connecting the transistor to the voltage divider circuit, okay? So what we're going to do is we're going to review voltage divider circuits for the first few minutes, and then we're going to analyze the transistor circuit. So I want to take you to page 13. Go to Appendix 2, page 13. Voltage divider circuits. Get a pen or pencil out. We're going to do some serious note-taking. We're going to talk about a type of circuit called a stiff circuit and a not stiff circuit. And we're going to explain what we mean by a stiff circuit. Okay? So, let's start off with case 1, a plain, regular voltage divider circuit. So case 1. What we show is a regular voltage divider circuit, R1, R2, VCC, 10 volts, 1K, and 1K. Okay? We know these circuits from our electricity class. We've talked about some of these circuits earlier in my class. And you will see these kind of circuits, especially the voltage divider circuit, over and over and over in your studies as well as in your line of work. Basically, the reason why it's called a voltage divider circuit is by having two resistors, you are dividing the voltage. In this case, 1K and 1K being divided into half, right? And so, if I was to take the voltage out at this point, what do you think the voltage will be? With R1, 1K and R2, 1K. It'll be 5 volts, okay? So, how do we get that? Let's write the equation. The equation of the voltage divider is probably as important and as popular and as widely used as Ohm's law. So, V out in this case is R2 over R total, R1 plus R2, times VCC. You've seen this before, right? Okay. So R2 is 1K divided by 1K plus 1K times 10, which is 1K divided by 2K times 10, which is how much? 5 volts. See? So we mathematically showed how we get the voltage split into 2, divided into 2. That's why it's called the voltage divider circuit. So the voltage is divided. So let's say you needed 5 volts to operate the device, but you had 10 volts. So what do? You use a voltage divider circuit. And so that's case 2. Case 2 is where you take the voltage divider circuit, but now you're going to connect something to it. A voltage divider circuit by itself is of no use. You're always using that with a lower voltage, such as 5 volts, to operate a device. So let's say the device I'm operating is a cell phone. Okay? And let's say case 2 shows that load resistor, and I'm saying that that load resistor RL is a cell phone, so I'll call this RL, and it happens to be 1K. Okay, so you can write cell phone besides RL if you like. So the plan is that I want to use this 5 volts, that's available to me based on the voltage divider circuit, R1, 1K, R2, 1K, and 10 volts here. I saw in case 1 that I get 5 volts out here, 5 volts. Am I getting 5 volts if I was to hook up a cell phone whose resistance is 1K? Let's see. Let's calculate V out again. The new V out is the resistance to ground divided by the total resistance times 10. So this time it's going to be, do you see that I have a parallel circuit here? So at this time it becomes R2 in parallel with RL divided by R2 in parallel with RL. I'm replacing this R2 with R2 in parallel with RL. And so it's R2 in parallel with RL plus R1 times 10 volts. Do you see what I did there? I have to find an equivalent resistance. So the equivalent resistance here is what? R2 in parallel with RL. So now I'm going to calculate V out given the load resistance is 1K. So how much does this become? 1K in parallel with 1K divided by 1K in parallel with 1K plus 1K times 10 volts.